End-frame assembly. The end-frame assembly, or housing, is made of two pieces of cast aluminium. It contains the bearings for the end of the rotor shaft, where the drive pulley is mounted. Each end frame also has built-in ducts, so the air from the rotor shaft fan can pass through the AC generator. Normally, a heat sink containing 3 positive rectifier diodes is attached to the rear end frame. Heat can pass easily from these diodes to the moving air, while the 3 negative rectifier diodes are contained in the end frame itself. Because the end frames are bolted together, and then bolted directly to the engine, the end frame assembly is part of the electrical ground path. This means that anything connected to the housing that is not insulated from the housing is grounded. Cooling fans. Behind the drive pulley on most AC generator is a cooling fan that rotates with the rotor. This cooling fan draws air into the housing, through the openings at the rear of the housing. The air leaves through openings behind the cooling fan. The moving air pulls heat from the diodes, and their heat decreases. Cooling the diodes is important for the efficiency and durability of an AC generator. Alternator operation. As mentioned earlier, AC generators produce alternating current that must be converted, or rectified, to DC. This is accomplished by passing the AC through diodes. DC rectification. According to these figures, when AC passes through a diode, the negative pulses are blocked off, to produce the scope pattern shown. If the diode is reversed, it blocks off current during the positive pulse, and allows the negative pulse to flow. Because only half of the AC current pulses, either the positive or the negative, is able to pass, this is called half-wave rectification. By adding more diodes to the circuit, more of the AC is rectified. When all of the AC is rectified, full-wave rectification occurs. Full-wave rectification for stator windings requires another circuit with similar characteristics. This figure shows a Y stator with 2 diodes attached to each winding. One diode is insulated, or positive, and the other is grounded, or negative. The center of the Y contains a common point for all windings. It can have a connection attached to it. It is called stator-neutral junction. At any time during the rotor movement, 2 windings are in series, and the third coil is neutral and inactive. As the rotor revolves, it energizes the different sets of windings in different directions. However, the uniform result is that current in any direction, through 2 windings, in series produces the required DC for the battery. The diode action does not change when the stator and diodes are wired into a delta pattern. Figure shows the major difference. Instead of having 2 windings in series, the windings are in parallel. Thus, more current is available from a delta wound AC generator, because the parallel paths allow more current to flow through the diodes. Nevertheless, the action of the diodes remains the same. Many AC generators have an additional set of 3 diodes, called diode trio. The diode trio is used to rectify current from the stator, so that it can be used to create the magnetic field in the field coil of the rotor. Using the diode trio eliminates extra wiring. To control generator output, a voltage regulator regulates the current from the diode trio and to the rotor. Voltage regulation. Voltage output of an AC generator can reach as high as 250 volts, if it is not controlled. The battery, and the rest of the electrical system must be protected from this excess voltage. Therefore, the voltage output from a changing system must be controlled. Current output does not need to be controlled, because an AC generator naturally limits the current output. The voltage regulator controls the voltage output of an AC generator. Regulation of voltage is accomplished by varying the amount of field current flowing through the rotor. The higher the field current, the higher the voltage output. By controlling the amount of resistance in series with the field coil, control of the field current and voltage output is obtained. To ensure that the battery stays fully charged, most regulators are set for a system voltage between 13.5 and 15.5 volts. The regulator must receive system voltage as an input in order to regulate the voltage output. This input voltage to an AC generator is called the sensing voltage. If the sensing voltage is below the regulator setting, an increase in field current is allowed, which causes an increase in charging voltage output. Higher sensing voltage will result in a decrease in field current and voltage until it is at a level to run the ignition system, while putting a low charge or trickle charge on the battery. If a heavy load is turned on, such as the headlights, the additional draw will cause a decrease in battery voltage. The regulator will sense the low system voltage and will increase current to the rotor. This will increase the strength of the magnetic field around the rotor and will increase the generator's output voltage. When the load is turned off, the regulator senses the rise in system voltage and reduced the field current. Another input that affects voltage regulation is temperature. Because ambient temperature influences the rate of charge that a battery can accept, regulators are temperature compensated. Temperature compensation is required because the battery is more reluctant to accept a charge at lower ambient temperatures. The regulator will increase the system voltage until it is at a higher level, so the battery will accept it and can become fully charged.